All right, good morning. This is 9:30 on Wednesday, the 29th of November, 2017. It's supposed to be Calculus 2 class, and right now I'm the only one in the room, which is not good, but hopefully y'all are coming. Let me go over a few announcements first. I think I made some of these before, but in case you weren't here and are listening now, hopefully you'll hear them. Number one, we really need your student course evaluations done, please. You don't have to do them right away. You can wait until even after you get your final grades, but I don't recommend doing that for the simple reason that I remember back when I was an undergraduate, and once I had taken that last final, I basically would turn the mind off and was heading home. And if I had had to do something else after that, it more than likely would have been forgotten. So don't be like me. If you are going to do that, be sure you do the student course evaluation after you see that final grade. I think probably all of you know pretty much what you're going to write, whatever your final grade is. So go on and do it now, okay? The sooner you do it, the better. I've actually heard it suggested not to give a final exam until the student course evaluations are done. I don't believe in that. That's sort of like blackmailing students or something like that. I don't like to do that. So if you want to wait to see your final grade to do the evaluation, that's your right to do so in my mind. So I don't know. I'll just ask you, please do them. I need all three of you to do them. They're shooting for 80%, and if only 2 of you do it, that's only 67%. So we've got to have all 3 of you. Please do the student course evaluations. Okay? Number 2, this is a new one that I didn't know last time, or didn't think about it too closely. I've got to go, well, back us up. I may have to go to the Birmingham campus this afternoon. Sorry about this. I've got yesterday, something about the room just got me sneezing, and I couldn't stop sneezing. And then my nose started running, and I couldn't stop it from running. As soon as I was out of the classroom, no problem. But that was all morning long. All 3 classes were just miserable because I was constantly sneezing and running nose. As soon as I left the room, all right, we have a student. Good to see. I think I even recognize him. Okay. All right. Good deal. If there's no students in here, I don't turn on the projector. No reason to. And I have the light switch. I'm already recording. So let me go back and save this. May not go back and check the recording now that you're here. The first was what I said last time. Please do the student course evaluation. Have you already done it yet? Not yet. Okay. Please get it done. Please. Number 2, and this was a new one. I may have to go to the Birmingham campus this afternoon. Now, this probably won't affect you any because you probably aren't going to be back on either campus. But normally my office hours are here on Wednesdays, Mondays and Wednesdays, 3:45 to 5:40. I mean 3:15 to 5:15 on Mondays and Wednesdays. However, there's some things that were supposed to have been done yesterday that I need to go over to the Birmingham campus and collect and process. Now, if they weren't done, I'm not going over there. But if they were done, I will be going over there. So when 3:15 gets here, I'm going down to my office, call the secretary, and see if the people did what they were supposed to do. If they did, I've got to go over there. So that means I'll just stay over there the rest of the afternoon. So I won't be back on this campus. But if they didn't do what they were supposed to, there's no reason for me to go over there. I'll have my office hours here. So I won't know until 3:15. But the odds are hopefully at least one of the people came by and did what they were supposed to do. So I'll need to go there sometime after 3:15 this afternoon. And then I'll just stay over there because it's a half hour, close to a half hour to get there, and close to a half hour to get back, so that'd be wasting half of my office hour driving back and forth. So I'm already losing a quarter of them driving over there, so I'll just stay over there and do my office hours there. Okay, that was new from, I didn't know to announce that last time. And the other one is one I did announce normally on Fridays, my office hours are 7:45 to 11:45. Not this Friday, because I've got an infusion. I'll be at the Kirkland Clinic from before 7 until probably around 4-ish or so. So not going to be on campus at all on Friday. Okay. And I think I told you last time, vote. Okay. Don't forget to vote. All right. All right. Let's set up from the current slide. Any questions on anything we've done so far? All right. So we finished 8.1, and that was arc length and that kind of stuff, surface area, that kind of thing. Now we're moving to, and these are, what we're dealing here is further applications of the integral. Okay. Chapter says and Taylor polynomials. We're not going to do those. We just don't have time to do them. So this is not quite the same picture you have in your book, but it's a similar picture. And what we're dealing with is fluid, pressure, and forces. Of course, these guys know about fluid pressures and forces because they're living with it and hoping to keep living with it, you know, because they could easily die from it if they didn't realize what was going on from it. Let me blow that up, and don't need to take too much time on it. But this isn't just an academic exercise. These are people's lives at stake here. Since water pressure is proportional to depth, divers breathe compressed air to equalize that pressure and avoid lung injury. Okay? Because when you're on the surface, you have just a little bit of pressure on you. The deeper you go. In fact, what's the pressure on you right now? Is there any pressure on you? You're completely without pressure, right?
If there is any, it's
What's that?
like if there is any, it's very so small that it's not really.
Actually, do you know what a square inch is? It's approximately your two thumb top joints like that. That's about a square inch. For every square inch of your body, you have 14.7 pounds on every square inch of your body. That's the pressure, pounds per square inch. Does that ring the bell? What do we have above us? Gravity doesn't have an atmosphere. Air. Oh, air doesn't have any weight, does it? Yeah, it does. Okay. You have 14.7 pounds of force on every square inch of your body. That's a lot of force. What's that? Yeah, because you have just as much pressure pushing out. In fact, you have a little more. If you prick yourself, where does the blood go? Out. Okay? So you're pressurized from inside, so you can equilibrate that pressure. Okay? Now that's one of the really huge hazards of the astronauts, especially if they do spacewalks and things like this. In fact, before the International Space Station was built, we at some point had a space station up there, but it lost its orbit and it crashed into the sea. We got several years of good use out of it, but we were left with the Soviet space station was the only space station left then. So we started cooperating with them, and we were helping them. But the Soviets didn't have the shuttle program like we did. We could deliver people supplies and stuff, and go back and forth. They just would send up cargo loads, you know, and they would dock with the thing. One of those dockings didn't go too well, and it mangled and messed up, and the folks in the space station had to then retreat to the innermost cube. I don't know how small that was, but it was not very convenient, I'm guessing. And they needed to be rescued, but they also needed to repair the space station. So we went up, sent up our shuttle, and we helped them, repair that. And I cannot think of any job that has ever been done that would have been more dangerous than that. Because what do those astronauts wear? Spacesuits. And why do they wear the spacesuits?
I don't like the pressure.
Okay, they're pressure suits because their bodies are used to about 15 pounds per every square inch of their body force on them, so they have at least that much pushing back out. And Juan decided to show up. Okay. And if out there in space, what's the atmospheric pressure on them there? It's negligible. May not be zero, but it's negligible. So if they would have had just a little bit of a rip in that, and just imagine, I will talk about the Soyuz Soviet space station before we had the International Space Station. It had been damaged by a cargo ship that collided too fast with it or something, and it mangled some of the ports and stuff. They had astronauts had to go out there and repair that stuff. Bent, broken metal, that kind of stuff could be very jagged. If they would have ripped their spacesuit on just a little thing of jacket, there goes all the blood and gases and everything spewing into space. From their eyeballs, their ears, every orifice they had. They would have been dead instantly. There couldn't have been more jobs more dangerous than many jobs more dangerous than that. And if that wouldn't have killed them, then the other thing the spacesuits does is reflect the radiation, because that's another thing our atmosphere does for us. It blocks the harmful gamma radiation and cosmic radiation, X radiation, all that really bad radiation. It keeps it from coming to Earth. Only thing that gets through our atmosphere is certainly the visible light spectrum. Thank you very much, because we wouldn't be alive if that didn't come through our atmosphere. But a little bit of ultraviolet rays come through too. And guess what they do to us? But what? They give you sunburn. They certainly do. What is sunburn, by the way? The radiation is literally burning the cells of your skin. Okay? And our skin can't handle the ultraviolet radiation. So out there's plenty of ultraviolet too. Sun gets through. Now there's actually a theory. I don't know, I don't need to get into this too much, but if you've ever read the Old Testament, the way early parts of it, some of those dudes they were claiming lived to hundreds of years old, 726 or something like that for Methuselah. And the people say, well, the years couldn't have been the same years. Well, that was before the flood. And if before the flood, we never had really any rain, we just had an atmosphere filled with water vapor, then the ultraviolet rays probably didn't get through, and who knows, those guys could have lived a very, very, very long time. But then once we got that water vapor out of the air, when the flood came, then after that, if you'll notice, reading there, you see the lifespans get shorter and shorter until it got to what we are. It's an interesting theory, you know. The ultraviolet radiation is what ages us because it damages tissue. Damages skin tissue, giving you sunburn. But repeated that over many years, what do you get? Skin cancers. There's several kinds. There's basal cell, which is the mildest. I've had at least one of those removed. I've got another forming. I put sunblock on it every day to keep it from getting any worse. There are some other one that is a little more dangerous than that, and then there's another one called melanoma, which is a skin cancer, which can be fatal. Just a skin cancer that can be fatal. We had a neighbor, a farmer I grew up in Georgia. She was 1 year older than me. We rode the bus together. We were pretty good friends. She died of melanoma. They found it, but they found it too late. It spread, and she went through a rugged several years fighting it, but they ultimately got it. So, not just that. What else happens to people who are out in the sun a lot, a whole lot, besides skin cancers? They get dark, And the reason for that, and you're luckier than we are, because you have a little bit more keratin, isn't it, in your skin, that you will darken up, and that's the body's way of trying to block that from getting to you. Okay, and you know, the darker your complexion, the more resistant you are to the skin cancer. Still gets to you, but it doesn't get to you as badly. But if you've ever seen those good old sun worshipers that were out there in the sun every chance they got, if you look at them today, like 20, 40, 60 years later, wrinkled. I mean, pretty badly wrinkled. It really damages the tissue. Another thing it does, I've had my right eye a cataract removed. Why did I have a cataract? The ultraviolet radiation going through the lens of my eye. Yeah. And if you live long enough, you're probably going to have cataracts because you're exposed to that. So just about all of our aging mechanisms, I think, maybe not all, I'm not a physiologist, but come from that. Now, how did I get off on that? I was talking about the good things the atmosphere does for you. One thing, what we started with, it adds pressure. And we are pressurized vessels. Okay. Well, when you get underwater, you're under more pressure. Oh, how high is our atmosphere? Anyone know? It's hard to define. It goes up for miles and miles and miles and miles and miles. But water is a lot denser than air, right? Did you finish?
Yeah, some I didn't know.
Okay, but you are finished.
Yeah, I'm finished.
Okay. So the grade I put down, I'll put in your book, right? Okay. Okay. All right. So, anyone know what 10 meters is? The ceiling here is about 3 meters, because I'm about 2 meters tall. I'm a little over 6, just barely over 6 feet, and a meter is slightly more than a yard, so that'd be a little bit more than 3 feet. So 2 meters would be a little bit higher than me, and then you've got almost another meter above me, so not quite 3 meters. But then you have some space in between. So the part of the building over there, the 3 stories, that's about 10 meters. Not that deep, but I mean, pretty good size. You go down 10 meters in water, you just added another atmosphere of pressure to it, an entire atmosphere of pressure to it. Go down another 10 meters, another atmosphere of pressure. Now 3 times what your body is used to. Go down another 10 meters, 4 times, okay, you add another atmosphere of pressure for every 10 meters of water, approximately, that you go down, okay? Now, therefore, these guys, and, you know, that's like a 3-story building. I don't know how far divers go without having to have really big pressure suits on. But if you go much deeper, at some point you've got to. Otherwise, you get crushed, okay? Your lungs, you don't have strong enough diaphragm to force air in and out, you know. And that's why they're talking about compressed air to equalize, okay? Now, that's just part of the problem. Going down isn't so bad. Coming up is worse. What's in your blood? Lots of stuff, by the way. But among other things, what's in your blood? Why is some blood blue and some blood red? Huh? Okay, oxygen and other gases. Oxygen isn't the only gas you have in your blood. You have what they call blood gases, right? Okay, now blood gases, and what's true about gases? As you increase pressure, yes, the volume decreases. That's Boyle's law, I think. Have you had that in physics yet? Okay, you'll have some of that. It's Charles' law, Boyle's law, and one other, I can't remember the name. But they are the ideal gas laws, okay? Increase pressure, you decrease volume. Which means that when you decrease pressure, you increase volume, okay? So, they dived down very deep, and the body adjusted to that as they went. When they're coming back up, though, they can't come up as fast as they went down. Because if they do, the blood gases that are in their blood all the action of your circulatory system? Where does really everything, the important stuff, take place? Okay, the heart is what pumps it, for sure. But what is it that turns that oxygen that's in your blood into something you can use to metabolize, to... Say again? Okay, the lungs provide the air. But what is it that I tell my finger bend? Okay, the nervous system tells it that. Where does the transfer happen? That the oxygen gets metabolized? It's in the capillaries, the very tiny, tiny blood vessels. That's where nutrients transport. That's where waste products are picked up. That's through the walls of the capillaries. Okay, capillaries are smaller than the. If you had it, I'm sorry. If I had it, yeah, smaller than a hair in diameter. Really tiny. And just think if you have a little bubble of air in that, and that's where the air gets transferred too. Oxygen goes through the muscles and the carbon dioxide comes out of the system. You know, that's where that transfer happens. It's in there. Well, what happens if you double the volume all of a sudden? Yes, you burst the capillaries. And where are the capillaries? All over your body. Your eyes, your ears, everything starts. You explode the capillaries. You don't live very long with exploded capillaries. Okay? It's called they actually call it the bends, because you get all cramped up, you know, all over in your body. That's happening, including in the lungs. Your lungs could literally explode. And that would be bad enough, but it happens all over your body. So yeah, pressure, depth, those people know what they better be doing. I heard someone coming. Okay, no. Okay. That was way too long, wasn't it? Okay. So, fluid pressure is proportional to depth. Okay? Now, how we express that mathematically is this. Let me get my pen activated. Okay? Pressure is proportional to depth. I was going to put a D there, but I noticed they're using an H, so let me use an H rather than a D. The height of water column above you. Okay? There is a proportionality. Have you ever seen that symbol for proportion? Okay. Looks like an alpha, it's not quite. Probably should have a little bit longer legs, but it's proportional. Well, you can change that to an equation by multiplying by a constant. It's called the constant proportionality. Okay? And the constant proportionality happens to be rho times G. Well, what is rho? Rho is the density of, the mass density of the fluid. Now, here in air, that's the mass density of air. Underwater, the mass density of water. If you were under mercury, hey, you're dead. But it would be the mass density of mercury. Times G, which is the acceleration due to gravity. Well, that's the number that's unique to the Earth, okay? So the pressure acts at each point on an object, like I was saying before, every square inch of your body, right now, is subjected to pretty close to 15 pounds of force from the atmosphere. If you were underwater, that would be increased to 20, 25, 30, 40, whatever, depends on how deep you are. So the pressure is proportional to the density of the fluid, whether it's a gas or a liquid, the acceleration due to gravity, that's the force pulling it down, and the height. Okay, now, just to get the units right, density is mass, which is like kilograms or something, per unit volume, that's density, multiplied by acceleration due to gravity, which is distance per time squared, right? And then by another distance, h, that's the distance. So that basically pressure, okay, this is mass per unit volume, so that would be length cubed, times acceleration, which is a length per time squared, okay, times another length, which is the height, okay? Why are the units not coming out right? Oh, okay. All right. Well, a mass times an acceleration, this is a force. Okay? This is a force. And then a length cancels one of those out, and that gives you force per unit area. Length squared is area. That's what pressure is. Force per unit area. So the units are working out right. Okay? Now, pounds per square inch. Force is pounds, square inch is an area. A Pascal is a Newton per square meter. Okay? Another force per unit area. So those are, so that's your definition of pressure. Rho, your density of your fluid, whatever fluid you happen to be in. G, acceleration due to gravity of whatever planet you happen to be on. And the height, how deep you are in that fluid. Okay. And that pressure acts on every point in your, every point on the object. Okay. So, our first example does not require integration because the pressure is constant. Okay, so if, like I just told you, pressure was force per unit area, then force would be pressure times area, right? And pressure would be rho GH. That's what pressure is. So now we got a pretty big, long, hairy term for force. Rho G H times the area. Okay. So let's do example 1. And by the way, just saying, y'all know what G is, don't you?
Gravity.
Okay. It's the acceleration due to gravity. Okay, little g is acceleration due to gravity. You know what value that has? Okay, on the Earth, 9.8 what? Don't ever give me a number without a unit. Meters per second squared. If you're dealing with U.S. customary, that would be 32 feet per second squared. Length per time squared. That would be the acceleration due to gravity. Okay, on the Earth. If you're on the Moon, it's totally different. If you're on Venus, you're dead. It would be very different. Okay. All right. So calculate the fluid force, we're looking for force, on the top and bottom of a box. Let's see if we can find this. Ah, here we have. Of a box of dimensions 2 by 2 by 5. So it's 2 inches long, 2 inches wide, those are meters. Okay. 2 meters wide, 2 meters long, and 2 meters deep. Okay. 2 by 2 by 5 meters, submerged in a pool of water with the top 3 meters below the water surface, as shown in this figure here. So 3 meters up here, 5 meters for the length of it, and we want the fluid force on the top and the bottom of the box. Okay? The density of water, rho for water, is 10 to, goodness gracious, where did that go? 10 to the third kilogram per meter cubed. Okay? Are you familiar with that density of water? Most of the time we think of density of water as being 1 gram per cubic centimeter. Right? I mean, yeah. 1 gram per cubic centimeter. You know why we got that? That's how they defined what a gram was. Okay, they come up in the metric system. They come up with what a meter was, and then they wanted something smaller, so like centimeters, and then you did a centimeter by a centimeter by a centimeter, which would be about like your centimeters, about like your little fingernail across. So one high, one wide, and one deep. That would be, or the little bitty cubes of sugar that doesn't really sweeten anything. That would be a cubic centimeter. And they said, let that be, that mass of water would be 1 gram. Well, when you expand up to kilograms per cubic meter, you wind up with 10 to the 3rd kilograms per cubic meter. That's why it's such a nice round number, because that's how they define gram was with that. Okay, so anyway, there's the density of water. Now that's pure water. Salt water would be a little more dense, and anything mixed in water would change the density a little bit. But that's pure water, we'll assume that. So we want the top of the box, okay? Now we want the force on the top of the box, okay? And what was our force? The last thing we had up there? Force is pressure times area. So it's pressure times area. But what was pressure? The previous one. Say again. Okay, so this will be rho G H times A. Okay? Now, I think we're ready to go. Rho for water is 10 to the 3rd kilogram per meter cubed. Okay? G was what? 9.8 units. Meters per second squared. G, that was G. H was, the top of the box is how deep? 3 meters down, so that would be 3 meters. And then the area of the top is 4 square meters. All right. So we want our force in what units? What's a good SI unit for force? Newton. Okay. What is a Newton? Kilogram meter per second squared. Force, mass times acceleration, right? F equal ma. Mass times acceleration. Mass in kilogram and acceleration in meters per second squared. So these units right here are going to be our Newton, right? All right. And notice here, you have a meter here, 2 more meters here, that's meters cubed. They cancel out the meter cubed there, so sure enough, we're going to have so many newtons, right? So the units are right. You can usually feel pretty good about the numbers working out well too, okay? So what you'll need to do is 12 times 9.8. Got a calculator? I'm sorry, we're going to do that in a minute. 113 what? 7 point what? 6 times 10 to the 3rd. There's my that. And this will be in newtons. So if you wanted to do that, that would be 1. Yeah, 117600 newtons. Okay, see what the book got. Look at that, they got it right. Okay, how about the force on the bottom? Okay, you do the same thing, only your H is now going to be 8. So that will be 32 times 9.8. Second? 313.6 times 10 to the 3rd newtons, which would be 313,600 newtons. And I think that's what they got to, did they? Good for them. All right. Now, that's because at the top and bottom you have equal pressure, so just multiply the pressure by the area as you get the force. All right. Good deal. Now, most of the time we don't have simple things like that. Okay? In fact, we're going to have the same problem here, but now what we're going to do is calculate the force on the side of the box. The top and bottom are easy because they're at equal depth. The sides are not at equal depth. This has less pressure on it than this does. Okay? So what we do, we split the only thing it varies by, not by the area down here, it only varies by the depth. So you want your delta y, if you're using y to be your vertical axis. So you calculate the say force or pressure. Calculate the fluid force on the side of the box. Okay? And what that's going to need to be is an interval. So we split the side of the book into increments of dy's. Okay? Your first dy is going to be y0 is going to be a 3, the last one's going to be an 8, and you have so many dy's in between. Now, they didn't say how much. So each area, each strip here on the side of the box here has 2 meters this way and dy 2 meters that way. Right? So its area will be 2 delta y. Right? The strip here, 2 delta y. And its depth will be y, okay? Because that's how deep it is from the water. That's what we showed. Y0 is 3, yn is 8, so any depth at your area is y. So your y sub j there would be 3, which is the top of it, plus j, how many increments you are down, times your delta y. The delta y is how thick each increment is, and if you've gone down j of those increments, j times delta y will give you your depth. That would be your y. Okay? So each strip has an area of 2 delta y, and each strip has a depth of y. I don't know why they go into that. It's just really y. Okay? That's your depth. Okay? Okay. Did you need that blown up, or can you see that well enough where you're sitting? You got it in the book too. Good. Okay? Now, what your summation is then, if you think of this, you're summing the forces on each one of those. Now, for some reason, suddenly I feel like it's getting warm in here. Is it for you? Or maybe my computer's just heating up. I was feeling pretty comfortable, and all of a sudden now I feel, I'm not sweating yet, but I'm hot. So anyway, we'll live with it. All right, so what we have here is your force is equal to, just like before, your pressure times your area, okay? And your pressure is rho g. Those are constants. H, your H in this case is your y, okay? And your area is, like we showed here, is 2 times delta y, okay? 2 because it's 2 meters wide. That's not a constant that's going to be in every formula. It just happens to be because it's 2 meters wide, the box is. So what you have now is rho g, I say g and write d. I don't know where that came from. Maybe I was going to change my delta to a d, but I wasn't thinking about it, but maybe rho g, those are constants, okay? And then we're going to integrate y. Oh, the 2 can come out here for this problem. That's not always going to be the case. 2y dy. And you're going to integrate from 3 to 8. Okay? That looks like it should give it to you. Let's see what we get. 2 times 10 to the third times 9.8. Now, I'm not putting my units down because the integration and stuff is here, but and anyway, this will be, what's the antiderivative of y dy? Over 2, evaluated from 3 to 8. All right, so let's just go on to make this 19.6 times 10 to the third times, and do that evaluation. Eight squared is? Second? What you get? Oh, you know what? Why don't we just do this? Wipe those two 2's out and just leave this 9.8 times 10 to the third. And what does that give you? 64 minus 9. Is that what you got?
Well, I just did it the other way. I got 27.5.
Okay. Let's see what we get this way. 9.8 times 10 to the third times 55. For some reason my pen is really, really slow. Okay. And what's 55 times 9.8? 539 times 10 to the third, which would be 539,000 newtons. Is that what you got? You got the same, but you did it a slightly different way. And guess what? They got it too. Good for them. I'm proud of them. Okay. What's that?
So that's the amount of pressure for each section.
That's force. That's what we're getting is force. And what's that again?
Is that for each section
Each.
or for the whole thing?
That's each side. That's one side. And you got 4 sides and they're the same, so multiply that by 4, that would be the total lateral pressure on it. So this is one side. That's why we use 2 dy, because that was just one side.
But so that's not for that one section.
No, that's what the integration does. You summed all of this. That's each section, and your integration sums them all. So integration does for you. It's really neat stuff, isn't it? Yeah. All right. So that gives you the entire side there. Okay. Oh. All right. Now, we add another complication. Good. That was too simple. Let's add another complication here. Allowing the widths of the horizontal strips to vary with depth. Okay? Such as this type of thing. Now, what does that remind me of? I grew up on a farm in Georgia, and we had cattle troughs that looked like that. Okay, so this might be the pressure on one end of the cattle trough, because that was, you welded that in, or it was welded in there, and the cattle trough was not exactly like that, but something. Why would you do a parabolic cattle trough? But that's what it reminds me of. Certainly not a nice square or rectangular or something like that. So your strips are varying with depth. Okay. So, can we do the same thing with that? I'll blow it up for you to see it a little bit better, but I can't write on it in this form, but I'll do that. So again, now they didn't tell us this was parabola, I just was guessing that. The area of the shaded strip, the shaded strip is approximately your F of yi, and they go into introducing this formula, function F, and I really don't see it helps that much. But times the delta y, and again delta y is the thickness, because in the small enough delta y, the pressure is going to be about the same. Y2K is coming down. Okay, so let's see if there's a problem here. So F sub Y is the width of the strip at a given depth Y. So that's what your F sub Y is the width of the strip at that given depth. So rather than make a formula, just go and calculate what those are. That's what we will be doing. This doesn't have a formula for it, just that. So let's see what the Theorem 1 tells us. It's basically building on what we were just talking about. Okay. The fluid force on a flat surface submerged vertically. Fluid force F on a flat side of an object submerged vertically in a fluid is, and we saw this pretty much before, rho g, those are your constants that come on the outside, the depth is y, and then they throw in this f of y dy, where f of y is the horizontal width of the strip at y. Why not call it w? Why call it f? You know, it would make a lot more sense to me to call it w of y. Okay? The object extends from the depth y is equal to a at the top down to b at the bottom. So depth is increasing as you go down. And you set up. This is unlike most of your physics problems where you have y positive, negative downward. This is y positive downward. Okay, so let's do example 3. Any questions on that before we leave it?
So that theorem was for the
Any shape. The f of y is taking care of the shape. That's the width. So why not call it w of y? I don't know. So let's do this one. Okay? This is simpler than a parabola. Okay? Fairly much simpler, I think. All right, example 3. Calculate the fluid force F on one side of an equilateral triangular plate of side 2 meters. Okay, got it. Equilateral triangle of side 2 meters submerged vertically into a tank of oil of mass density rho is equal to 900 kilograms per cubic meter. Denser or less dense than water? No, it's actually less. Remember, it's 1,000 was the density of water. This is 900. Okay? So a little bit less dense. Oil floats on water, right? Okay. So there is the figure. Now, I call it f of y. What is the width of any depth here? What is the width? There, all the way down. What is that width function? As a function of depth. Well, we knew that the side here was square, that was 2, right? Equilateral triangle, that means that's a 2 and that's a 2. But, what is the y value at the base there? Okay? It helps me, oops, I can't write on that, I forgot, to imagine a perpendicular dropped here. Okay? That makes this 90 degrees, that 90 degrees. That makes this 1 meter. These were meters, weren't they? Yeah. 1 meter and 1 meter. Equilateral triangle is also an angular triangle. So what's each of the angles there? Second? Oh boy. 60. 3 angles of a triangle have to add 180. Divided by 3 is 60. So this is 60 degrees. The whole thing would be 60, but that bisects it, so each one of these would be 30 degrees, and this is, of course, a 90 degree. Okay? So with all that in mind, and also realizing that this lateral distance length is 2 and that one's 2. Okay? Now, we just came up with, believe it or not, a right triangle, right? 30, 60, 90 triangle. This side is 1, that side is 2. What side is that going to be? Square root of 3. That's really not square root of 3. But you knew that all along, didn't you? Okay, good. All right. So that's the depth. That's the maximum depth. Now, at any depth y between 0 and root 3, those are going to be the limits of this. What would be your length here? Down here it's 2. Up here it's 0. What's the width at anything in between? With anything in between, you've got a similar triangle here. It's just that you have shorter sides. So this will be the length of this side. And of course, that side shorter, that side shorter. So you still have an equilateral triangle. So that's still 60 at the top and 60 on the side. So it's still an equilateral triangle. So what is that y? How can we deal with that? Okay. Are y'all familiar with similar triangles? The ratios of the sides have to be the same. So we know that big triangle there has a ratio. What do you like? You want it? I don't like F. I want to call it W. W is to Y as, what's the W down here? 2 is to square root of 3. Do you buy that? That for anything here, the width here is to the depth there, as the width here is to the depth there. Similar triangle, right? So that gives you the width as a function of the depth, which would be W is equal to 2 over root 3 times Y. So there's your width as a function of depth. They call it F. I like to think of it as width. I see width better, okay? I'm just sort of weird, okay? Very weird. You shouldn't be agreeing with that. I was supposed to hear protests. I didn't hear a single one. Thank you very much. Okay. All right. So I think we're ready to roll then, aren't we? What is the force? The force is equal to rho, which was 900 kilogram per meter cubed, G, which I think is still 9.8 meter per second squared, times the integral of remember it's M, G, H, your H here, your depth here is your Y, okay, and the width, that's the thing we don't know, that's your F or your W, and that is 2 over root 3, so I'm going to put the 2 over root 3 here, times Y, which would be Y squared now, right? dy. Okay. Well, let's see if this makes sense. I think it does. Because your force, this is your Newton right here, kilogram meter per second squared. Here you have per cubic meter. These are just ratio, that's just numbers. And here you have a meter times a meter times a meter. So that gives you cubic meters. So those will cancel these out, and that gives you a force. Feels pretty good, doesn't it? Okay? So, what does this give you? Oh, let's see. What's 1800 times 9.8. Punch that in on your calculator.
17,640.
Okay, that's everything. And did you divide by root 3 already? Okay, divide that by root 3.
101.84. 10,184.
Okay, 10,184. I'll take your word for it. I'm a little hesitant to, but I think I will, okay? And then what's the integral of y squared dy? Okay, evaluated from, oh, I didn't put my limits in. What were they? At the top, it was 0, and at the bottom, it was root 3. Okay? So this will be 0 to root 3. Okay? Belay that, folks. I'm going to change here for a moment. Okay? I'm just going to multiply the numbers together. And what did you have before? That was 1800 times 9.8. 17,640 over root 3. I hope you see why I'm doing it that way. Okay? All right. Now, when you multiply this out, y, substitute in root 3, you get root 3 times root 3 times root 3, right? Yes? Right? That would be 3 times root 3, right? So this will be 17,640 over root 3 times 3 times root 3. Right? Divided by 3. Notice the sound effect. Okay. And the root 3's go out. So what are you left with? 17,640 newtons. Oh, look at that. 17,640 newtons. Okay. When I realized I was going to have a root 3 in the numerator, let's not get rid of the one in the denominator. Let them cancel out. That way you don't have to be multiplying and dividing by two numbers. And then, surprisingly, the 3's cancel out. Yeah, this worked out really nice. Does that make sense? Okay. Now, for some reason, the f of y's do nothing for me. But if I think of it as a width, yeah, I can. That makes more sense. Okay. That was example 3. Let's move on to example 4. Let's see if that's in here. I think it is. All right. Now, these are same picture. I mean, same thing that it's picturing, but definitely different times of year. Okay. This was the one in the old edition. It must be spring. And it's taken from a slightly different elevation. The one in your book from a little bit higher looking down. This is one when everything is green. Okay? The one in your book, everything is brown. Now, I don't know if they had that big a drought. I mean, I don't know. I can't account for that. But it's the same thing. There's the road in front, the dam behind. You know what the lake behind this is named? Lake Mead. Pretty sure that's the lake behind that. Now that doesn't maybe look all that impressive now, but at the time when it was built, I think this was the largest dam in the world. Now, I think the Chinese have built one bigger, and maybe several other people have too. But this was an enormous, enormous dam. So that may look sort of small to you. It's not. I mean, that is huge. The depth of that is incredibly deep. Here's how deep it is. Sometime after World War II, we were still had a lot of people in the military, and they had developed a lot of planes really quickly during World War II, and some of them worked really well, some of them didn't work all that well, but they were just trying to get them out there fighting the Japanese earlier, the Germans, but mostly the Japanese, and they had some pretty bad planes, okay? And one of those planes was on some sort of a training run, and I believe it was maybe during World War II or slightly thereafter. And it was doing night training and was doing it over Lake Mead, and it crashed into the lake. Excuse me. They never investigated much to fish it out or anything else. But does anyone know what? Okay. Lake Mead certainly produces hydroelectric power, right? For a lot of the western U.S. I think Los Angeles, a lot of Southern California gets the power from that. But that's not the only thing they get from that. The water backed up here, they use for irrigation. And what happened out west for the last 7 years or so? And what caused the fires? Drought. Really, really, really bad drought. They had been pumping so much water out of the lake. Number one, they weren't getting as much electrical generation because that's where you get that potential energy of the water going through that became electrical energy. So they weren't cutting down on that, but they got deep enough. It sank so low that they found the plane. That's pretty scary. Now, they did have some pretty significant rainfalls in the last year or so, so you wouldn't be able to, if it's still there, you wouldn't be able to see it anymore. But that was pretty scary. They caught that low of water. But that's beside the point. All right, force on an inclined surface. The side of a dam is inclined at an angle of 45 degrees. Now, that's not this dam. This is a theoretical dam. Here's what we've got. This is like one of your engineering projects, right? Huh? You guess, yeah. Sort of like an idealized thing, okay? So let's say that it's inclined at 45 degrees. And by the way, they need to do that because there's more pressure at the bottom than there is at the top, right? So there we have that. So the side of a dam is inclined at an angle of, my nose is dripping again, sorry, 45 degrees. The dam has a height of 700 feet. And you see there, 700 feet there. Now we're down to feet again, not even meters. Okay. The width is 500 feet as shown here. 1,500 feet as shown here. Now, to me, I would have put that back here. You see all the other numbers here. Out front here just looks out of place. It's the same. And this is not the Hoover Dam that does like this, This is just an idealized thing. Okay. Calculate the force F on the dam if the reservoir is filled to the top of the dam, full 700 feet. Water has a weight density. Now, here's something different. In the U.S. customary system, they use weight density, not mass density. So, guess what you don't have to deal with now? Weight is what kind of quantity? No, mass is mass. Weight is a force. So you don't have to do mass times acceleration. So you don't have the acceleration of gravity if you're dealing with weight density. Because weight already is included. Weight is the force. Mass is not force. Mass is mass times acceleration, accelerated gravity. That's what makes the force, okay? So this one, you don't have G involved. The weight density is 64 62.4 pounds per cubic feet. Okay, they don't have that on here, so I'm going to have to shrink this. So your weight density is 64 pounds per cubic foot. Now that's going to take the place of rho, not just of rho g. W is equal to rho g. That's what I was trying to get at. This is rho g. What was rho g before is W now. Now, I don't like that because usually you use weight W, little w for, sorry. Weight, not weight density, but I guess we can live with it. This is a math book, not a physics book. Okay, so you're calculating the force on the dam if the reservoir is filled to the top of the dam. All right. So now the force is delta y. I mean, the depth is delta y, just like we did before. So you're now going from 0 at the top to 700 at the bottom. That limits your integration. Your delta y is your thickness of each one of these. And because it's a 45-degree angle there, let's just assume 1, 1, this would be square root of 2. So that would be square root of 2, that delta y would be the surface area of that. Okay? So now your that's what your delta y divided by sine 45 is that. Sine of 45 is root 2 over 2, or 1 over root 2, and so that would be root 2 times delta y. So that's where you get that. I'm not sure you need that, but that's what you get. So let's see what you got. Calculate the force on the dam if the reservoir is that. All right. So your force, what was your formula again? Force equal? Second? Pressure times area. P times A. And what's your pressure? Okay, that's your rho G is 32.4 times H, which is going to be your Y now, and the area. And the area here is they're saying square root of 2 delta Y, I'm thinking. Yeah, the square root of 2 times delta y. Okay? So let's get all in terms of y. Okay, but remembering our rho g is our w. Okay? So your force is equal to w, and you can bring the square root of 2 out there too. Square root of 2 times w times the integral from 0 to 700, this is all in feet, of okay, yeah, y dy. Now let me make sure this is making, yes, yes. Because this pressure is, remember pressure is force per unit area, and so this is force per unit area because it's a weight pressure, times an area, y times dy is an area, that will give you a force. So we're okay, unit-wise. Make sure your units make sense. That means your numbers fairly reasonably should make sense. All right. So what does this give you? root 2 W. Well, we know what W is. Let's start with 64 pounds per cubic foot. I'm still having problems with that unit. Okay. Yep, that's exactly what we got. Just doesn't seem like it. Okay. Oh, that's the other part we're missing. All we did was depth and how far down you were and the delta y. What we forgot is our width. We need that in there too. That's part of your area. Okay, the area is length times width. Your length was your dy, or root 2 dy, so you need your width there too. And that width is, I would have put a W there, but they're using W for something else. This is your 1500. So that's also in the picture there. I forgot. I knew we were missing a dimension. That's why I said this, I'm having problems with it. So this is times 1500. That's the width of the dam. And that would be in feet too. So putting the units in. And then you integrate that. What's the integral of y dy? Y squared over 2. Very good. And that's going from 0 to 700. Right? Now, let's take the 2 out of the picture here and make this a 32 here. Okay? And that will give us 32 times 1500. Goodness gracious. Someone got a calculator? Okay, multiply that by root 2.
67,000.
Say again?
67,882.
82?
125.
Let's just round to that, okay? Times, and then when you plug this in, that would be 490,000. Okay. I think we got some pretty big numbers here, folks. Okay. So do 490,000 times your 67,882.5 or whatever you had there. What do you get?
3.326 times 10 to the 10.
And that unit would be pounds. We've been in U.S. customary this time. All right, they got 3.24. Ooh, 24. How'd they get that? Oh, I'm sorry. I see how they did it. Somehow I dropped. Sorry about it. It's 64.2. 62.4. 62.4. I just wrote that down wrong. So you have to go back here. 62.4, and if you divided 2 into that, you get 31.2. Okay, so you'll have to go back and change the numbers, but didn't change it by a lot. What does that give you? .24, they say. Times 10 to the 10th pounds. That's a lot of force, folks. A whole lot of force. No wonder they're thicker at the bottom than at the top. They go through your standing time. And that is the total force. So yeah, you got to have a really good base down there. All right, that finishes 8.2. Want to do preliminary questions or not? Huh? Preliminary questions or not? Yeah? Okay. Number one, how is pressure defined? Okay. Force per unit area to me. That's as simple as I would want to do it. Force per unit area. I don't know. See what the back of the book does on it. It seems like a silly question for a math book to be asking, but let's see what it does. This is 8.2. They may not even give an answer here. Pressure defined as force per unit area. That's exactly it. Okay? All right. Number two, fluid pressure is proportional to depth. What is the factor of proportionality? I call it the constant proportionality. What would you say that was? Okay, from the very beginning, we said pressure is proportional to the depth. Okay, we'll use Y now. I was using H or D before. Well, what was that constant proportionality? Pressure is equal to rho G, H or Y. So there's your constant proportionality. The product of the density times the acceleration due to gravity. That would give you force per unit volume, I think it is. Yeah, something like that. Okay? So that's what they're getting at. The factor of proportionality is the weight density of the fluid, which is the mass density times the acceleration due to gravity. Number three, when the fluid force acts on the side of a submerged object, in which direction does it act? Strange sort of little question there. When the fluid force acts on the side of a submerged object, in which direction does it act? It basically is perpendicular to the surface. So if the surface is like this way, if it's like this, it's that way. It's perpendicular to the surface is what I think they're getting at here. Fluid forces act in the direction perpendicular to the side of the submerged object. That's why we had the root 2 in there, in this one. All right, number four. Not much math in these, Arthur. Why is the fluid pressure on the surface calculated using thin horizontal strips rather than thin vertical strips? Sort of an interesting. Yeah, because the pressure is changing vertically, it's not changing horizontally. As long as the strip's thin enough, then you can approximate constant pressure. Vertical strips, you got the same problem you had to begin with. Changes up and down the strip. Very good. Let's see how they express it. Pressure depends on the depth and does not change horizontally at a given depth. That's saying the same thing we did. Number five, if a thin plate is submerged horizontally, then the fluid force on one side of the plate is equal to the pressure times the area. Is this true if the plate is submerged vertically? No. Same reason we did before. When the plate is submerged vertically, the pressure is not constant along the plate, so the fluid force is not equal. Okay. Homework exercises. Do it looks like do any of the odds 1 through 23. Okay. You pick and choose. I do some of the simple ones and then do some maybe that were a little more complicated. Okay. I don't think they gave us the Hoover Dam's height. But they have in the problem on page 455, number 21, the massive Three Gorges Dam on China's Yangtze River has a height of 185 meters. Okay? Calculate the force on that dam, assuming that the dam is a trapezoid, blah, blah, blah. Interesting little problem there. Okay. Now, let's do a little bit in the next section. I'm not absolutely certain we'll do it all. Any questions on that section before I leave it? Okay. I'm sorry. Did I tell y'all about the strange phenomenon I'm experiencing? Yesterday morning, over the weekend, overnight, morning, everything, I just felt perfectly fine. Came into my 8 o'clock class yesterday morning. I got about halfway through the class and just started sneezing almost uncontrollably. And with that came drainage, almost uncontrollable. And it happened the rest of that class. I went out into the hall, went to the restroom, went down to my office to get something. Once I left the classroom, dried right up. In the restroom, in the office and stuff like that. Came back for my next class at 9:30. Hadn't been here 15 minutes. Started all over again. After that class, went to the, in fact, I may have had to break in the class, but in between classes, went to the other restroom, went to the office, his stuff. What's going on here? As soon as I was in the room, dried up completely. Quit sneezing, everything. Had my third class, 5 minutes into that class, thing, all class long. I had to stop the class twice and go get more tissue because they were soaking wet. I mean, it's all gross, you know. And then after that, I had lunch and then a 2-hour office hours. As soon as I went, ate in my office and stuff, dried up, never sneezed, never had anything for those 3 hours, not a thing. Then I taught for another 2.5 hours in this, or 2 hours in this classroom in the afternoon, not a thing. Came in this morning, overnight, nothing. Came in this morning. Shortly into the class, started having a little bit. Only sneezed a time or two and only filled 1 wad, you know. But that's why I'm draining again. I don't know what it is. But as soon as I leave the room, it quits. I thought I was catching a cold, but it doesn't seem to be. All right, but anyway. This is center of mass. Okay? Something I would never do. Do your SEALs or your coaches have you doing things like this? I'm glad. Okay. This acrobat was Cirque du Soleil, which is Circus of the Sun. I think it's French. Must distribute his weight so that his arm provides support directly beneath the center of mass. That's why that leg is sticking out that way, the other arm is this way, his other leg is some other way. He has to be sure that his center of mass is directly over the arm. If it's not, crash, bang, slam, okay? Out of there. If I were on a flat surface, I could not do that, yeah, but never mind that. All right. So what we're going to talk about here is every object has a balance point called the center of mass. Okay? They do use another term here. In the section, we'll use integration to compute the center of mass of a thin plate, also called a lamina, where it has a constant mass density. It gets a little more complicated if you have things that are not constant mass density, but a thin plate will usually assume that. Now, my first time I ever remember anyone referring to a center of mass, back when I was in probably junior high school or something like that, I believe it was, some Olympics shortly before that time, the U.S. won the gold medal in the weightlifting in the heavyweight division with a guy that lived the next county down the road from where we lived. his name was Paul Anderson. He was one strong dude, okay? And he was also a motivational speaker, pretty much from a Christian perspective. And he would come talking about, and he went around to schools and did things like this. And what he would typically do is have them set up some pretty sturdy platform, wooden type platform, and have the class sitting on that platform. And it would be set up on sawhorses or something like that, and pretty tall ones too. They'd have to walk up and get on that. And these would be little kids, like grammar age kids. And maybe a class of 20 or 30 kids, probably the teacher too. And he would then, after he had given the talk and stuff like this, or maybe before or during or whatever, he would crawl underneath there and lift the entire class and the platform. He was one strong dude, okay? But his point was he couldn't do it unless he knew where the center of mass was of that object, because anywhere else he tilted. How he did this, I don't know how they did it. I never was in a class they did, but he would go and I guess he would test different ones, and when he found the right sweet spot, then he would lift them. And that's where I first got the concept of center of mass, sort of like this, but even on a bigger scale. Okay. And I don't know if the next slide is on here or not. I don't think it is. The one in your book does have a slide. And why it's a Green Bay linebacker, I'm not sure, and a ballerina with the New York City Ballet. I mean, Green Bay must have been playing the Jets. I don't know. But anyway, why did they choose ballerina? Why did they choose linebackers? I don't know if you've ever been to a ballet. I haven't, but I've seen a few on television and stuff. Those are the ones that fly around, and stuff. And if they do, the guys throw them up and lift them and stuff. So they're usually pretty lightweight, right? And Green Bay linebackers are usually pretty heavyweight. Okay, so there's a distinct weight difference there. If they were playing seesaw, y'all used to remember doing that? Okay, teeter-totter, some people call it, out in the playground. The linebacker is going to have to shorten his end, and the ballerina on the other end, but at some point they can find the balance point. Now why? Because Archimedes, way back, by the way, let's see, papers. Got 2 out of 3 in. Guess what, team? 1 weekend left. This is it, folks. Okay? It's last chance. Okay? Get in there without losing points. Okay. But anyway, you can find that point. I always had to shorten it because I was the heaviest one in the class back then. And always had to shorten if I was going to seesaw with somebody. I didn't get it up and down very much. The other guy or gal did. But as Archimedes realized over 2,000 years ago, the mass of each object times the distance to the balance point must be equal. Now, Archimedes did it with the thing of a lever, and that's the thing. In this case, her mass, m1, times her distance from the fulcrum, has to equal his mass, which is much bigger than hers, times his distance from the fulcrum, therefore it has to be far less. Okay? And so, that reminded me of something else. Oh, yes. This is it. Can you lift a car?
No.
You can. Weakling. Bailey said he could. You can. And you work at a dealership, right? You've never taken a jack?
Oh, man.
Oh, yeah! Why can you lift a car then?
I'll
thought you said like me, myself, with my hands.
Well, don't you use your hands on the jack?
I guess.
Okay. There's nothing else. It's just you lifting. That's the only force. The jack's not providing any force. You are. The jack provides what they call a force multiplier, because why? Your hand goes up and down probably several feet, and the car goes up a few inches. Same as this. The linebacker and the ballerina can balance because mass times distance equal mass times distance, or force times distance equal force times distance. Yes, you can lift a car. Archimedes' famous saying, I assume he said it, but it's attributed to him. He said, "Give me a fulcrum to place it. Give me a lever long enough and a fulcrum to place it on, and I could move the world." And I guess he could have. Of course, he would have had to have somewhere to stand too, but that, yeah. All right. Now, they do a little calculation here. I wish we had the gal, the ballerina, and the football player. But let's say the total length let's do that calculation there. Here's your fulcrum. Here's your mass 1. Here's your distance 1. Here's, I should have made this mass 2. And this will be distance 2. Okay? So, here's your origin. Okay? This is going to be your x1 here. This is going to be your x bar here. That is your center of mass. This is going to be x2 out here. Okay? Now, what we just said was M1 D1 is equal to M2 D2. If that was R2, it would be a little robot, real cute, but not that. Okay. So let's put this in terms of x's. Okay. What is this x1 here? It's x1. So what is the D1 here? I guess that's how I should say it. D1 here is equal to x bar minus x1. Would you agree to that? Okay. So this is now going to say M1 times x bar minus x1 is equal to M2 times what? Well, that's x2, D2 is equal to x2 minus x bar, right? Agreed? X2 minus x bar. Okay, I can't speak right. Okay. x2 minus x bar. Okay. Now, what we're going to do is a bunch of manipulations. None of them too complicated, but just some manipulations here. And by the way, the x bar is called the center of mass. Okay? CM or COM or whatever. So let's multiply through M1 x bar minus M1 x1 is equal to M2 x2 minus M2 x bar. Right? Yay, nay? Okay. Yay. All right. Now let's get all the x bars on one side. So what we're going to do is add an M1 x1 to both sides. And we'll add an M2 x bar to both sides. Okay? These go out, those go out. So what we have now is M1 plus M2 times X bar, that's what we got here, right? Pretty exciting stuff, huh? Is equal to M2X2 plus M1X1. And then divide both sides by M1 plus M2. And there we have what the center of mass says. X bar is equal to M2X2 plus M1X1 over M1 plus M2. Okay. Now they wrote the X1s first, and you know the M1X1 plus M2X2 doesn't matter. Now that's called the center of mass. Now let's think about what that means. That means that the have you gotten in the moments yet in engineering? Isn't that what we call a moment? A mass times the displacement. Yeah. So this is the moment, the sum of the moments divided by the sum of the masses. Have you hit that yet?
We're doing like moment of inertia.
Okay. Yeah, well that's a little more complex than this. Yeah. But you'll both probably get there to something like this. I think that's in statics or dynamics. I don't remember which. Have you done one of those yet? No. I think you'll probably get there. Okay. The quantities M1X1 and M2X2 are called the moments, and then of course the M1, M2 is the masses. Okay. So let me clear this slide. No, wrong key. Wrong key. Okay, this key. All right, let's look at this. This is figure 3 and figure 4. See, they didn't have the ballerina and the football player, okay, in the old edition. They put them in the new one because they were such a clever idea, huh? All right. If this is your point up here, okay, and you're in space here, two-dimensional space here, this point here, it has a mass at this point. It's located at this value xy. This has a moment with respect to the x-axis, and that's your my, okay? The moment with respect to the y-axis is your m times x. Mass times distance. Mass times distance. So they call it m sub x, but it's m times y. You call the m sub y, which means moment with respect to the y-axis, m times x, because x is the distance from the y-axis. So it's a little bizarre seeming. It seems a little backwards. So generally, I try to not even mess with the terms moment. You know, I don't find it helpful. I wasn't an engineer. Engineers work with moments all the time, so I'm sure they're going to keep that nomenclature. All right. But that's talking about that. Now let's talk about this situation. Here we have 4 masses, and mass 1's up here, x1 distance from the y-axis, and that happens to be a negative distance. M2's over here, and x2 distance from the y-axis, which happens to be a positive x2. M3's over here, x3 distance from the y-axis, which happens to be negative again. And M4 is over here, x4 distance from the y-axis, which in this case happens to be positive again. How do we determine the center of mass of those 4 objects? Okay? Well, we add all the moments together and divide by their masses, just like we were doing before. But here you've got 2 dimensions. Now, what they didn't show was your moments with respect to the y-axis. Okay? That would be m1 times y1, and positive m2 times y2, m3 times y3, m4 times y4. And you have to get a center of mass in the x direction and the center of mass in the y direction. But do them separately. Don't mix them up. So let's see if this sort of makes sense. Now, I think by the size of the dots, we're going to assume all those masses are the same. Okay, the only reason they give subscripts on them is because to let you know which goes with which distance. Well, this is a pretty small distance. That's a further distance. That's further than this, but not by much. But this is even further still. So obviously, your x component of the center of mass is going to be to the right side in the positive way. Well, all masses are above the y-axis, so it's got to be up here. These two are above, these two are below, so the center of mass is going to be somewhere in that. You do sum your moments divided by the sum of the mass, and that will give you y component. So there's your center of mass, is where those two intersect. Okay? Now, I think they give this, yeah, here it is. I was hoping I wasn't going to have to do this. Okay. Now, the old edition called it XCM and YCM, X component of the center of mass, Y component of the center of mass. Now, they left off the moments, but we already did the moments, if you remember. Okay? And it just seems sort of backwards, but it doesn't seem as backward if you actually wrote out what the moments were. If this is mass 1 times x1 plus mass 2 times x2 plus mass 2 times x3, add out all those, and these are the M1, Y1, M1 to Y2, add all those together. If you put the distances there, these are x distances, those are y distances. So you have something that M times x is M times x, M times x, add those together, add the masses, the m's, you can think of it dividing out, and that gives you x's. So to me, it's just almost more complicated to throw in the sub y's and sub y's, but the engineers love it. So just keep in mind, it works a lot better. Oh, are we out of time? Yuck. Okay, we'll start next time with example 1. I think when we're actually doing the examples, hopefully you'll see that the situation sort of makes sense. Okay? So we'll pick up in there. Let's see, did we get enough to do any homework exercises in this section? I kind of think not. Let's just hold off until we do example 1. All right, good deal. What are we doing this weekend? Paper! Okay, good deal. And nothing like procrastination until the very last weekend, huh? Yeah.
Yeah, that's what I got so much to do.
I know. I can't imagine that the instructor didn't say at the beginning of the class, you know, you'll never have more time to do it than right now. If you had a good instructor, he would have said that. Too bad. You lost again.
It gives me extra motivation to do it when I have a little short time to do it.
Yes. All right, take care. Have a good weekend. We'll see you.